So given a triangle ABC and a point P, I can compute the antipedal triangle, this red thing here, of point P with respect to ABC as follows. Each vertex of this antipedal triangle is simply the meet of these perpendicular lines here, defined as you basically draw a line from P to a given vertex, you compute the perpendicular passing through that vertex, and then you do the same for another vertex, and where they meet, that's a vertex of the antipedal triangle. Okay, so you get that. Now, I've extended or generalized that to a polygon. Well, let's look at the picture on the right here. Take a polygon, n-gon of some kind, and let's take two adjacent vertices, vi and vi plus 1. So all I'm going to do is I'm going to take from a given point P, I'm basically going to compute these two perpendicular lines, shown as dotted red lines or segments, and where they intersect, I'm going to call that the antipedal point or vertex of point P with respect to this side here, vi plus 1. And then I can repeat this for every vertex, for every side of the polygon to get a set of pi primes, the antipedal points, which are going to draw up the antipedal polygon, okay, which is not shown here. But I just want to focus on this one construction here. Now, why am I showing this? Because I've stumbled upon a very interesting phenomenon that I'm showing over here. And it's the following. If you take a regular n-gon, in this case n equals 7, okay, and a point P anywhere in its plane, and then you compute those n antipedal points, so they're shown here as these orange points here, they're going to fall in a conic for whichever P in the plane. So for example, let me go ahead and move P around a circle here, this dash circle. This is actually illustrating that another phenomenon, that the eccentricity of the conic that passes through all these 7 points, okay, it doesn't change. And it's only related to the distance from P to O. Now P always falls, P is not the center of the conic, but it always falls on the major axis of the conic where the antipedal points fall. Okay, so for example, if I change that radius here, you can clearly see that P is not the center of the conic, nor is O a focus of the conic, okay? But it looks like the major axis of the 7-point conic is PO. Now if I increase the number of edges to 8, okay, you keep getting the same result. So now I have an octagon, okay, still have 8 points that pass through that green conic. Let me go ahead and change the position of P here. Let's place P outside of the polygon. Okay, now there are some positions of P where your conic is actually a hyperbola. Okay, so this is the conic that passes through the n antipedal points of P with respect to sides of this regular polygon. Okay, you can see here that, again, as P is moving around a circle, and I believe this conic here is I believe this is a right hyperbola, but I would have to check. I haven't done this exploration yet, but the main result here is that the n antipedal images of P with respect to sides of this regular polygon, they follow in a conic. Now, the really cool result is if P moves along the incircle of this regular polygon, the conic is a parabola. So, I really like this result. Let's go back to, say, n equals 5, okay, which is the minimum at which you can compute 5 antipedal images and then get a conic. Okay, now as I move P around, the 5 points, let's try to put all of them on the screen here, one position of P. As such, I can now see 5 locations of the 5 points. I can just break the symmetry a little bit, like so, and put it like there. Oh, yeah, so the phenomenon here is that I'm getting a hyperbola, okay? But what I wanted to show you is if R is on the incircle of this regular pentagon, then that conic becomes a parabola. And what I've noticed also is that you can see here that two of the edges of this antipedal polygon are passing through two vertices of the pentagon. Let's see if this is the case for n equals 6. Let's put it on the incircle of n equals 6, and you can see here that yes, I'm still passing through two vertices. I still have a parabola as P moves in the incircle. And it looks like I'm always picking, by symmetry, right, two vertices. So for example, now I'm passing through this vertex here and that vertex there. Let's go to n equals 7 and to see if we get the same kind of situation. Yeah, it looks like I'm passing one edge of my antipedal polygon is passing through a vertex of my regular heptagon, and the other one is passing through that as well. I'm still getting a parabola. Why am I saying this is a parabola? This is purely experimental. If I take this guy out like that, you can see that this conic never closes, right? So why is this a parabola? Just by eyeballing this, it looks like a parabola. Now, if the circle about which P is rotating, so where's the focus of this parabola, right? We can just, by looking at this, just inspection, we can say that the focus of this parabola, which is going to lie somewhere around here, okay, is going to be describing a circle as P moves around, I believe, because I'm just rotating this parabola rigidly. Okay? Parabola is getting rotated rigidly. I could use GeoGebra to plot the focus, or I could just do some more mathematical hacking here to see the locus of the focus as P rotates about this incircle. What happens if P lies on the circumcircle? Now here, this is giving me some numerical instability. When P is on the circumcircle, I don't know if this is correct, but as far as I can tell, all the points, all the antipedal points, if P is on the circumcircle, they become the antipode of P. They congregate at the antipode of P. Let's just perturb the radius of the circle by a tiny amount forward. So I have 1, let's make it be 1.01. Yeah, so you can see here that this is correct. If P is on the circumcircle of a regular n-gon, all my antipedal points, vertices of my antipedal polygon, they congregate at the antipode of P. So now I've just perturbed it slightly outwards, and now you can see here that I'm back to a hyperbolic situation. Let's perturb it a bit more. So I have a hyperbola, and as I move P around, okay, I get this hyperbola. I'm just eyeballing this, and I would guess that the eccentricity of these hyperbolae do not change as P moves along a circle centered on O. Now, if I start moving P inward, that hyperbola at some point becomes a parabola at the incircle case, okay? I think this is the transition from hyperbola to parabola, and then if I go in, it becomes an ellipse. So I'm slightly inward now, and now I can scale out and see that indeed this thing closes to an ellipse, right? So it's a finite conic. But when P is made to pass through the through the incircle, which I can achieve just by jogging this guy forward, okay, you can see that this ellipse becomes ever more bigger, okay, and then at the point where I'm exactly at the circumcircle, I get the parabolic situation. Is that clear then? So all I'm doing in this video is I'm investigating the vertices of this generalized antipedal polygon, okay, using this construction here on a regular polygon. Okay, I'll see you on the next video.